Okay, this is the second part. I'm going to probably call it refraction part 4, but it's second part to 13.2 in your book. So, one thing I forgot to mention here was when this equation pops down just about here, when we had the n equals c over cs in your book, you've also got the equation which makes perfect sense where you've got your n. Oh, now I lost my pen. The n is equal to lambda over lambda s. Therefore, isn't going to be the ratio of the wavelength as well. And it's all to do with the fact that this equation here is c equals f lambda. If c goes down, lambda goes down in the same amount. So that's where that equation, that one comes from. Now, this proof here is not too bad at all. Now, this diagram is not bob on what's in your book, but I'm going to use it. So what you've got here is I'm going to call that the angle of incidence. There's your normal line. And therefore, here's going to be your angle of refraction just here. Now, this can be any sum to whatever it is, and it's got refractive index of n1. Now, what I mean by that, as a refractive index is like air into that substance. So this could be water. It could be whatever it is. And this one is going to be glass, and that's the refractive index of that substance. Therefore, when the light travels through there, it's going to have a speed of c1. And when light goes through this one here, it's going to be a speed of c2. Okay? Now, with that then, I know is the refractive index of going from medium 1 going to medium 2, okay, where you're going to have your sine I over your sine R. And that was a terrible R, wasn't it? Try and make it better. And that's refractive index going from 1 going to 2. And sometimes what we do is you write down n and do 1 to 2 equals, because I'm going from 1 to 2. But I know from the previous work we've done, that obviously then equals C1 over C2. Well, I'm going to now use this equation here. Now, it then makes sense, there's a bit of fiddling around, if I can then take 1 over C1, therefore I'm bringing the C1 down here, then that's going to be sine I. Then take that up there, isn't that going to be 1 over C2, and that's going to be sine R. And all I've done is taken that one over there and that one over here. Then I'm going to simply multiply it all the way through by C. C over C1 equals sine I equals C over C2 sine R. Now, why have I done that? Well, the bits I'm interested in here, as I'm interested in that one just there and that one just there, because that's the refractive index from that substance, because it's going from air into that substance. And that comes from the equation before was n equal to c over cs, which is actually the same as c over c1. Therefore, the final part of the equation pops out here. It's a very, very useful equation. I'll make sure I write exactly the same way in the book. Yeah, I'm going to do it. Is that one is going to be n1, refractive index of that substance. Sine I is then equal to that one, which is n2 sine R. You'll find it in your formula sheet, but this is, and don't worry whether they've written it down here, it's a different notation. That is an absolutely critical equation. Absolutely critical, because that's the one you use all the way through refractive index. And it's going to one you can never use is going to be that one there. And basically that cracks 90% of all refraction questions. So this is the sort of things they can ask you. Now, I'm not going to bother with this part here. These you'll find in some of the questions, and they're on the next page or so. Yeah, they're on page 192. And this bit we've done already is about working out the speeds going through. But the bit I'm interested in, this bit here, is you've got, first of all, in this question here, is you've got light travels from a boundary from water into glass. So here's going to be your normal. Missed that there now, and there's the light coming in like this. It's going to then refract towards the, like that one here, going through. And what it's doing now is I'm going from water and I'm going to glass. And because the refractive index is bigger, the glass is going to bend towards the normal. Because here you've got the water is given as 1.33 and your glass is going to be 1.52. Greater refractive index, therefore it bends towards normal. So you've got the angle I here and your angle R just there. As I show, the angle of refraction, which is down here, is 46 degrees. So you go into N1 sine I equals N2 sine R. And therefore, N1 is going to be your water, 1.33. You then put in your sine I, and the angle of instance, in this case of here, is 55 degrees. Then you've got your N2, which is going to be 1.52. Sometimes they quote it 1.5, but hey, they're going 1.52 here. And then you've got your sine R just over there. Now, rearrange the equation then, if you start plugging it away through, is I then know my sine R is going to equal to 1.33 multiplied by sine 55 degrees divided all by 1.52. Now, if you bung that in your calculator, you get the sine I equals 0.72. If you then inverse sine that, you'll find then the angle R pops out to 45.8 degrees. Looking at significant figures, we've got 2, therefore won't then R equal what they said is 46 degrees. And that's how you use that equation. Again, use the principles, formula working, answer units. Now, what I want you to do is I want you to wipe out all these summary questions here. I want you to do the whole lot of them. And that one just popped up here. This is actually from the new book, which some of you have, and that just been through that part of the question just there. And I want you to go through 1, 3, 4. We're going to put the answers on Edmodo for you as well. Also, what we're going to put on there is this exam question here. Now, this one, making it a bit bigger, this is what it builds up to. What you've got now, make it a little bit smaller again, is where you've got a, well, it's like a big glass bowl, isn't it? You've got now got a layer of oil and you've got water. And this is what they will start doing. Light comes on straight through here, goes along normal. Here's the angle of incidence, there's the angle of refraction. And you need to start working them out where they go through. And the answers to all of these are going to be very, very nicely down here for you. So I just realised that total internal reflection pops out in this one. We've not done that yet, but you can start working through it and you can actually go through, you're probably get down to part B. Upload it anyway, and some of you want to carry on with total internal reflection, you can just keep going. That's not a problem at all. But have a so well, I'll go through that in the next lesson. TIR, total internal reflection. Anyway, you can answer all of those just there. Now, the last thing to mention was, as linked to here, this was going all to do with bending of light. And this is where it comes out, light comes through, you start seeing all different colors come out the prism. I have mentioned this before in the last video, but to recap what I mentioned before is the fact if light comes through the prism, the fact that the amount of bending also depends on the wavelength, and that comes back from the equation that I showed before, that the refractive index is n equals lambda over lambda s. Therefore, different wavelengths get slowed by a different amount. In other words, we can go all the way back here, find it, that equation there, that is dependent on the wavelength as well. And obviously red has a different wavelength or longer wavelength of violet light. So to summarize, what I've done is I've been through, go back to my pen, is you can now work out the refractive index using the ratio of speeds and ratio of the wavelengths. You can now use that equation and explain why white light is dispersed by a prism. Hope you enjoyed the video.